This reduction of order problem looks a little bit monstrous, but actually it works out really well. So to actually create these, what you do is you come up with your first homogeneous solution, you make up a difference equation that it satisfies, and then you try to play around with the coefficients until you get a second homogeneous solution you can actually solve for somewhat easily. But here we go. So here's the made-up equation with the homogeneous solution it was made for, and we're going to try and find the second homogeneous solution using reduction of order. This one's not going to be very fun, but let's do it. So we have y2, right, we guess, is equal to, y2 is some unknown function v of x times y1. Okay, well, I write that as v times the natural log absolute value of x. Now we got to take some derivatives. So we get y2 prime equals, let me fix that prime. All right, so v prime times the natural log absolute value of x plus v, the derivative of natural log absolute value of x, that's 1 over x. All right, I'll leave that alone. I can't really simplify it. Then we have y2 double prime. Okay, well, we'll get v double prime times natural log absolute value of x. That's the first half of the product rule from this first term. We have the second half, so we'll end up with v prime times derivative natural log. So that's 1 over x. Okay, now onto the second term, so I'll get v prime times 1 over x. Then the other half, I get v times, so this is really, right, x to the negative 1. So if we take the derivative, we'll end up with a negative 1 popping out. X to the negative 1 turns in x to the negative 2. So it's negative 1 over x squared. Can't simplify that a whole lot. Oh well, so let's keep going. Next step is to plug y2 into the differential equation. So we're going to be a little short on room here, so I'll just do here, let's see, x squared natural log absolute value of x whole thing squared times y2 double prime. Oof. All right, so we've got, I'm going to put the x's in front of the v's, so we'll get natural log absolute value of x, v double prime. Then I've got a plus 2 over x times v prime. Yeah, that looks right. And then we got a minus v over x squared. Okay, that's the first term. Now I've got the minus 2x natural log absolute value x times y2 prime. All right, well, that's natural log absolute value of x times v prime plus v over x. All right, then the last term here, I've got 2 plus natural log absolute value of x all times y2. So that's just natural log absolute value of x times v. And now all has to equal 0 from the original ODE. All right, let's try to simplify this. All right, I've got x squared, natural log squared, then another natural log, so I have x squared natural log absolute value of x cubed times v double prime. All right, then I've got 2 over x times x squared, so that's going to be a plus 2x. Yeah, times natural log absolute value of x squared, all times v prime. Then I've got a negative v over x squared times x squared, so that's just going to be a minus no x's. Then I have my natural log absolute value of x squared. That's all times v. All right, hopefully we have enough room. I've got minus 2x natural log absolute value of x times natural log absolute value of x, so minus 2x natural log absolute value of x squared v prime. Then I've got minus 2x natural log absolute value of x times v over x, so that's going to be a minus 2. The x's cancel there. You get natural log absolute value of x times v. Yeah. Then we got plus 2 natural log absolute value of x v plus, then I've got natural log times natural log, so that's natural log absolute value of x squared v. That's all supposed to equal 0. Alright, and here's the magical part from the coefficients. A bunch of stuff will cancel out. So let's take a look. I have my x squared natural log absolute value of x whole thing cubed v double prime. But now I have a 2x natural log absolute value of x squared times v prime, but I also have a minus 2x natural log absolute value of x squared v prime, and those actually cancel, so I have 0 v primes. Alright, and I also have a minus natural log absolute value of x squared v. I also have a plus natural log absolute value of x squared v, so those cancel. I also have a minus 2 natural log absolute value of x v. Then I also have a plus 2 natural log absolute value of x v. Those cancel, so I also have plus 0v equals 0. So my differential equation, which really isn't a differential equation anymore to solve, is x squared natural log absolute value of x cubed v double prime equals 0. But if we look at this, right, so we could get this whole thing to equal 0 if x is 0 for the x squared, but then we can't plug in x equals 0 for the natural log absolute value of x. So that's no good. And then natural log absolute value of x equals 0, I think, when x equals 1, right? But then that won't fix there. So what we're going to try and do is we're going to just say v double prime. We could also, just divide it over. So v double prime equals 0. So now we're going to solve that differential equation. Not too bad. If you do solve it, right, we integrate once. We're going to get to, and let me do that down here. So we have v double prime equals 0. We integrate once, so integral v double prime dx equals integral 0 dx. Okay, well that ends up leading to v prime equals a constant. Then integrate one more time. Integral of v prime dx equals integral some constant c dx. Well, that leads to v of x is equal to a constant times x plus some other constant. So in the y2 we originally had, I'll squeeze it in down here, we have, I'll put it up here. So we originally had the y2 was equal to v of x times y1. In our case, that's end up, if we blindly plug it in, it's some constant times x plus some other constant, all times natural log absolute value of x. But right again, if we multiply that out, we end up with cx natural log absolute value of x plus d natural log absolute value of x. This thing right here is already y1. And we don't care a lot about constants. Right, we want to make this as, y homogeneous solution equals c1 y1 plus c2 y2. So again, right, we just want to look for the new unique function that we've solved for. So we're going to actually pick out this piece, right? That's the new unique function. So we're going to choose that y2 is just this x natural log absolute value of x. So we don't have this redundant y1 in there, and we don't have to use redundant constants from the c1 and c2. So if we choose y2 equals x natural log x, then the homogeneous solution is c1 times natural log absolute value of x plus c2 x natural log absolute value of x.